RF receiver design. Fig.2 shows a block diagram of the proposed UWB receiver. Signals are received and filtered by the off-chip antenna and the RF radio frequency, filter firstly. And then the received signals are amplified and converted to IF intermedia frequency, baseband signal by RF front-end building blocks. After further filtering and amplifying, the analog baseband signals should be large enough to drive the ADC for digital signal processing. The receiver's local oscillator, low, should be a fast-hopping frequency synthesizer that generates carrier tones according to the band plan in Fig.1. Performances such as in-band phase noise and referenced spur are specified as -80 dBc and 40 dBc respectively, which are not so stringent. And the IQ mismatch is designed as 2.5 degrees and 0.2 decibels. Normally the noise figure of channel select filter is around 30 decibels, thus the conversion gain of RF front-end building blocks should be larger than 30 decibels to suppress the noise from LPF low-pass filter. But in that case, the linearity of the receiver will get worse. In order to improve the linearity of the receiver, the conversion gain of the RF front-end building blocks is set to be around 24 decibels average, with variable gain of 12 decibels. The NF noise figure of the LPF is designed to be less than 18 decibels to guarantee low noise of the receiver. The Lna Low Noise Amplifier utilizes a fully differential structure and presents an input matching to 50 ohm for the off-chip antenna. It should provide a maximum gain of 18 decibels to suppress noise from mixer and baseband circuits. As Lna sets the baseline for the noise figure of the receiver, the NF of the Lna should be optimized to lower than 5 decibels. Following is a quadrature mixer with a fixed gain of 6 decibels. The fifth-order Chebyshev type band selection LPF is implemented after the mixer. Unlike normal channel select filter, the proposed LPF should provide a maximum gain of 30 decibels, with a NF less than 18 decibels at maximum gain mode. According to the Friese equation, the noise of the LPF nearly doesn't contribute to the total input referred noise of the receiver, leading to a very low noise figure. As the back-end block of the receiver, the filter tackles with slightly large signals, leading to stringent linearity requirement for the filter. Since the filter suppresses adjacent channel interferers to some extent, the linearity of the filter is proportionally improved. Sharp rejection of out-of-band signal is also required. Considering the difference between the sub-band's bandwidth of two standards, the cutoff frequency of the filter is switchable between 264 MHz and 132 MHz. Finally, the PGA, Programmable Gain Amplifier, amplifies the signal from the LPF and delivers constant magnitude signals to the ADC. Architecture of the proposed receiver. Attaining an input impedance match with a wideband receiver is particularly difficult because parasitic may dominate the input impedance network. Fig.3 gives a presentation of the Lna for the proposed UWB receiver. A resistive shunt feedback topology is adopted in the Lna design, which achieves a wideband matching with a good balance between area cost and performances. Although there is a slight degradation of the noise figure comparing to other techniques like LC ladder, Bevilacqua A. et al., 2004, and transformer feedback matching, Shindi H. et al., 2007, quite a large number of inductor coils are avoided. Bonding wire inductance bonding and the ESD, electrostatic discharge, capacitance together with the pad capacitance CP8 are co-designed with other on-chip components. The load stage is an RLC tank. The load inductor LL can be replaced by a differential inductor to get a smaller area. However, we split it into two symmetrical inductors for convenience of cascading with mixer in the layout. A fully differential topology is utilized in Lna design to have the input impedance match independent of the bonding wire inductance from the source of M1 to ground. Fig.4 shows the simulated S11 with different bonding wire inductance. Schematic diagram of low noise amplifier. Simulated S11 with different bonding wire inductance. Fig.5 shows the folded Quadrature down conversion mixer for the UWB receiver. A fully differential Gilbert cell base structure with IQ branches sharing the same RF input stage is implemented in the mixer, which eliminates the mismatch present in down conversion topology with separate IQ mixers. Exploring merged architecture, Stoland H. et al., 2003, for the Quadrature mixer can also minimize the capacitive load to the LNA. Compared with the traditional structure of mixer, the folded structure utilized in this work separates the input stage and switching stage. Thus different bias current can be applied to the input stage and switching stage, better performances are achieved. The bias current of the input stage is bigger to guarantee good performance on conversion gain and noise figure. On the contrary, small current in the switching stage can lower the 1/f noise and DC offset, which is significantly important in zero-if receivers. Quadrature down conversion mixer circuit. The main difference between the two standards is that the intermediate frequency is 4.125 MHz to 264 MHz and 1 MHz to 132 MHz for WE Media MB OFDM and China UWB standard respectively. In order to support both standards, the cutoff frequency of the band select filter should be switchable between 132 MHz and 264 MHz. Using two different filters to support each standard may be a possible solution, but will sacrifice a lot of die area. Furthermore, as the first stage of a stage, the NF and linearity of the filter should be optimized. Thus the LPF should provide variable gain to suppress noise substantially at maximum gain mode and meet the linearity requirement when set as minimum gain. In this work, a fifth-order Chebyshev type programmable GMC filter is implemented. The fifth-order low-pass filter is realized by a cascade of a first-order RC filter and two biquads. The proposed architectures of the low-pass filter and the biquad are illustrated in Fig.6. Note that the down conversion mixer's load resistors are utilized to form the first passive RC filter stage. As a result, simulations covering both the mixer and the filters should be taken to make sure that the overall frequency response and gain are optimized. The modified NATA GM cell, as shown in Fig.7, is implemented as the OTA operational transconductance amplifier, in the filter. The transconductances of all the OTA are controlled by the digital data. Structure of the low-pass filter. Modified NATA OTA. The topology of the PGA, Programmable Gain Amplifier, is based on a source-degenerated structure as illustrated in Fig.8. A switched resistor array is implemented to achieve variable gain from 0 dB to 18 dB with 2 dB/step. High gain amplification easily causes the following stages into saturation due to DC offset, and DC offset also leads to second-order harmonic distortion, HG2, of the received signals, resulting in SNR signal-to-noise ratio degradation. Thus the DC offset cancellation circuits are also included in the PGA design. The amplitude response of the PGA is designed to be flatness within the frequency range of 264 MHz. Topology of the PGA.